Today's a little bit like that first day, if you've ever been to a camp or even the first day of school, when you get to know some of the neighbors, maybe the neighbors at your table group. You find out what they're into, what colors they like, what sports they play. Those are some of the things that we're going to be doing, except for instead of meeting new people, we're going to meet different types of reactions that we're going to be working with and running into. And the cool thing about what we learned today is that we actually get today to where we'll be able to make some predictions. We'll be able to say, somebody will be able to say, oh, hey, we mix hydrogen and water and what would happen, or we mix sodium and water and what's going to happen, or we light this chemical on fire. Is it going to burn or is it not going to burn? So these are the types of things that we can, at least at a little level, start to predict based on a little bit of what we've learned today. Okay. So the first thing here, these are the types that we're going to come across. And I know it's a little hard to see some of this because some of it's covered up, but one of them says synthesis, decomposition, single replacement, double replacement, combustion, and neutralization. So there's going to be 6 different reaction types we'll talk about. All right, so talking about these different types, here is a summary. I'm going to take a quick photo of this. I'll do this on a lot of these, where I'll take a quick photo and, one second here, just take a quick photo and so I can write on it. So in this case, okay, this page is just essentially an overview of the different types of chemical reactions. And so I'm going to use a metaphor that is kind of a relatively easy one to work with, but you can imagine kind of a high school dance. This is maybe more of like a traditional high school dance, not where everybody's just jumping around out there, but where people are dancing with each other and how different people, how those dance partners might change as that night went on. And so you can think about this maybe like as prom or something like that, and all the drama that could happen at prom. So the first one is what we call a single replacement. So a way to look at this is you've got 2 different ions dancing with each other, and you've got a metal over here on its own. And then what happens is the metal says, essentially comes over to this couple and says, can I cut in? Okay. And then what happens here, you can see that after the reaction, now the C is now dancing with A, okay, and actually the metal has now become an ion, and B is on its own. So this is essentially a story. Somebody was on the side, asked to cut in, and then the dance partner says, yes, you can cut in, and then B gets left on its side. Kind of a sad story, but that's kind of what happens with single replacement. Now, double replacement is a little bit less of a sad story. You have A dancing with B and C dancing with D. And then what happens is they decide, hey, maybe this arrangement could be better because one is looking at somebody else in the other couple, and then another is looking at somebody else in the other couple. And if you look what's happened here, when we get to the other side, A is now dancing with C, and B is now dancing with D. So this is kind of a happier story because, yes, there was a switch that took place. Things didn't go as planned, but people are more or less happy at the end of the day because we made this switch, okay? Now, we also have some other simple stories. This is 2 people standing on their own that then meet each other, and now they are a couple. This is called a combination reaction. A combination reaction is just 2 different substances that combine to form a compound, essentially. Now, decomposition, another kind of sad story here. In decomposition, we have chlorine and sodium, and as the night goes on, they realize they have too many differences, and they break apart, they decompose, okay? Now, combustion doesn't really fit the metaphor so well, but combustion is one of the more exciting types of reactions. What's actually shown here is what happens on our stoves. They don't actually show, this should be CH4, they don't show that correct. But what happens here is you take a compound that usually includes carbon and hydrogen, and you combine that with oxygen, and you form CO2 and H2O. In the process, you give off a lot of heat. Okay, it could be heat and light and everything else. So this is what's called a combustion reaction. With a combustion reaction, you're looking for actual substances. Oxygen is one of the reactants. Carbon dioxide and H2O are always the products. And so that's what happens on our stoves. That's what happens in our fireplaces. That's what happens in our vehicles if you have a combustion engine. Obviously, if you have a battery, it's a little bit of a different case. And then finally, neutralization. This is actually a acid-base reaction. And what happens is you take an acid, and the way we're going to know that we have an acid is anything that has an H to begin with, okay, with the exception of H2O. Other than H2O, anything that has an H to begin with is an acid, okay? So HCl is an acid, And then a base is anything that has OH in it, okay? So when you see OH, like NaOH, sodium hydroxide, or any other magnesium hydroxide, potassium hydroxide, all of those are bases. Now, I will tell you, there's more to that story, but for our purposes, that fits most of the cases that we'll ever see. Okay, in an acid-base neutralization reaction, the reason they call it neutralization is because you have this dangerous acid, hydrochloric acid, you have a dangerous base, sodium hydroxide. But when you combine them, the hydrogens combine with the hydroxides to form this harmless substance called H2O. And also another harmless substance called NaCl. So this is something I would never recommend, but if you were very bold and you were in a scenario where you had to make a bet or something like that, you could perfectly match up the exact same amount of hydrochloric acid and the exact same amount of sodium hydroxide, mix them together, and you would have harmless salt water that you could then drink to show that you were somehow a wizard or something like that. But that would be something that you could do with a neutralization reaction. Okay, now getting into a little bit more detail, the combination reaction, there's also two other names that you'll commonly see for this. Sorry, I was going to click that, but I can't do it. Okay, you'll also see synthesis and formation. I actually haven't seen formation much, but synthesis is a very common name for a combination reaction. In fact, I think it's even more common than combination. And all we're really saying is that two substances react to form a single new substance. Okay, again, two people find each other, and now they are a couple. Okay, so in this case we have, and when I say two, obviously you can have two of sodium, one of chlorine. It's not dependent on exactly how many you have of each, but two different substances essentially come together to form a compound. So obviously one of the most common ones here is sodium and chloride, or I'm sorry, chlorine gas. When sodium and chlorine gas come together, they form sodium chloride, salt. Okay. Another one here is we have sulfur trioxide combining with water to form what we call sulfuric acid. Okay, and so this is something that can actually happen in our this can actually happen in, I believe this happens in our atmosphere when we have acid rain. I need to confirm that, but there is a reaction that happens that's very similar to this that can cause acid rain. So then we can predict the product if we know the starting elements. Okay, so if we have magnesium and nitrogen, question is, what element do we, or what compound do we form? Okay, so I just posted that little starting of a reaction onto our notebook. So we've got magnesium and nitrogen, and we actually can use our skills that we used when we were learning how to name compounds in order to figure out what compound this forms. So we know that magnesium wants to form Mg2 plus. We know that nitrogen wants to form N3 minus, and then we decide, well, what combination are those going to come together? And obviously we're going to get Mg3 N2. Okay, and hopefully that makes sense. We know that we need two of these. We know that we need three of these in order for the sides to be balanced. Some of you like to do this process. I'm not a huge fan of it, but some of you like to just switch the numbers. Again, that works about 90% of the time. So it's good just to know the limitations of it. So that would form Mg3N2. And then, of course, we just need to balance this chemical reaction. We need to put three of these, and we would have a balanced chemical reaction at that point. And so this is what we call a combination reaction, meaning we have two substances combining to form one substance. Okay, so that completes a synthesis or combination reaction. Now, the next type of reaction is called decomposition. And decomposition, what we're doing is we're taking a single compound that breaks down into two or more simpler compounds. And so what you're really looking for is something on the left-hand side that doesn't have a plus in there, and then something on the right-hand side that has a plus, showing that we now have two different substances. Okay, so here's one example is two mercury oxides becoming two mercury metals and an oxygen, essentially, or calcium hydroxide breaking into calcium oxide and H2O. Anytime we have one thing on the left and then two on the right, we're going to have a decomposition reaction. I'll just mention that decomposition is very common when it comes to things that are rotting or deteriorating over time. A lot of that is decomposition reactions. Okay, the next type of reaction is called single replacement reactions. And we also call these single displacement. And just to review, what happens here is we've got C sitting here on its own, and C says, hey, I want to cut in. And what happens is B says, okay, yeah, you can cut in. And now B and C over here are dancing with each other, and A is left on its own. There are some problems with this picture. The way they did the colors didn't work correctly. But nonetheless, the idea hopefully is clear. Somebody's on his own or her own, cuts in, and now we've got two people dancing with each other and one person on their own. But there is one other piece to the story, and it might sound a little bit cold and calculating. When C says to B, hey, I want to cut in and I want you to dance with me instead of A, B is, like you said, a little bit cold and calculating. B actually has a card. And on this card, it's what we call the activity series. And so B looks at the card and pulls it out and says, okay, let me look where C is and let me look where A is. If C is higher on my card than A is, then I'll make the switch. If, on the other hand, C is lower on my card than A, I will not make the switch. Okay, and that's how this happens. So in the case of this reaction that we see above, the same thing would occur here, where nitrate then is the dance partner, the dance partner everybody wants to dance with here. Copper and nitrate are dancing with each other. And then zinc says, I want to cut in place of copper. Okay, and then what happens here is nitrate pulls out his list or her list, whatever, and looks on that list and says, well, let me see where copper is. And I know it's a little bit hard to see here, but copper is right down here. Okay, and then zinc, on the other hand, is way up here. So nitrate says, oh, well, zinc is definitely an improvement. I'm going to make the switch. Copper then gets left on its own, and zinc is now dancing with nitrate. And that's how the story goes. All right, you might wonder who is trying to replace who. Well, if there is a metal dancing with another non-metal, okay, and a metal wants to come in and cut in, only metals can replace metals. Okay, you can't have a metal replace a non-metal. We could also have the other side of that, where, and especially this happens in halogens. Okay, so halogens, we're talking like fluorine, chlorine, and bromine and iodine. Everything there to the second to last group in the periodic table. With halogens, it will be a halogen replacing a halogen. Okay, so you're talking about the anion replacing the anion, essentially. So, but a halogen could not replace a metal, and a metal could not replace a halogen. That really wouldn't make any sense because we'd end up with a plus and a plus, or a minus and a minus, which would repel, as you know, with all of the electrostatic forces. Okay, so a couple other things here. Elements that are higher up are more reactive. So elements like lithium and potassium and calcium, these are going to react almost every time. They're always going to find a way to cut in. Okay, but the elements that are, so this is one example, just like what we just showed. Zinc is replacing copper because zinc is higher up on this activity series. But then if an element is way down here like gold, gold almost never reacts. That's why you actually find gold in nature in pure gold, because it doesn't react with anything else. It stays on its own, or it will react with very few things. Gold does react with some things for sure, but it's not that common, and that's why you can find it in nature on its own. Okay, now the next type is double replacement reaction. And again, this is, like I said, just a little bit happier story, but there is actually more to this than just like how it sounds. They're not just switching partners. There's something that drives this, and here's what's happening here. So in this case, you have NaCl, which is salt, with something called silver nitrate, okay? And these are just they look like two liquids that we have. And so they with some color in them and everything else, but they are solutions like salt water and silver nitrate. They're both in solution. You mix them together, okay? And what happens here is you form a solid. This is really what drives the reaction. When silver and chlorine run into each other, they are no longer soluble. So all of a sudden you mix two solutions, and we'll do this in one of our labs. You mix two solutions, and all of a sudden a cloudy substance starts to form, and that cloudy substance kind of slowly drifts out of that solution and falls to the bottom. And that cloudy substance would be the silver chloride. And then what is left in the solution is sodium nitrate. So what really drives this whole reaction is the fact that silver chloride is not soluble. So when those two ions meet each other, they hold together very tightly, and they're no longer attracted to the water molecules, and so they slowly fall out of solution, and then you get this kind of a collection, or what we call a precipitate, on the bottom of the beaker or in the bottom of the test tube, and that tells you that this double replacement reaction has occurred. I do want to make note of this statement over here because this is important to note. In fact, my head might be in the way. I don't know if I can move that. Sorry if my head's in the way. It says, if a solid does not form, we write no reaction. Okay, so if there's no solid, okay, then the reality is there's not really any exchanging, because if there's no solid that forms, then really all we have is just a bunch of ions all floating around. We just have 4 ions all floating around in solution. So the fact that a solid is forming is why we even consider this a reaction. All right, the next type is something called combustion. Combustion is a chemical reaction where oxygen is a reactant. So in this case, in all of the other ones, we haven't really specified what those substances need to be at all. Okay, they could be all different types of substances. But with combustion, it's really, we're talking about a very specific type of reaction that involves certain substances. Okay, and here is what you're going to look for when you're trying to identify a combustion reaction. Oxygen will be one of the reactants, just like it shows here. Oxygen's a reactant. CO2 will be one of the products, and so will H2O. So we have oxygen as a reactant, CO2 as a product, and H2O as a product. Now, I will tell you there are some other reactions that are considered combustion that aren't exactly like this. Okay, oxygen pretty much always is a reactant, but sometimes you get some different things over here. But in general, for all of the ones that you guys will see, we're talking about oxygen as a reactant, carbon dioxide, and water as products. So when you see oxygen as a reactant, carbon dioxide as a product, and H2O as a product, you think combustion reaction. The other thing that you'll notice in this reaction is that one of your reactants usually is a combination of carbon and hydrogen. Like this case, it's methane, which is CH4. You could have ethane, which is C2H6. You could have propane, which is C3H8, or some other ones. Octane, which is C8H18. So all of those are examples of different hydrocarbons or carbon and hydrogen combinations that you could have as a reactant. Now, you could actually have some things that are that include oxygen as well as a reactant, but usually it's carbon and hydrogen that you're looking at. So you can see all of these examples below. These are all combustion reactions, and some of these you've already seen in your balancing chemical equations examples, like this one here. This is octane combined with oxygen to produce CO2 and H2O. And another thing you'll notice, a lot of times these are very big numbers here that you have to make all of these balance. You've already seen this a couple of times in our examples. Okay, now finally, I believe this is finally, neutralization reactions. Neutralization reactions are also called acid-base reactions. Now, we have talked very little about what an acid is and what a base is. So just to give you a very, very brief overview here, an acid is just anything that when you put it in water is going to release H plus ions. So an acid is really just an H plus ion combined with an anion. Like this example over here, HCl, which is called hydrochloric acid. The H is like an H plus, and it's combined with a chlorine, a Cl minus, and when you combine those together, it is called an acid. Okay, now technically it is not a ionic compound, though it's very close to an ionic compound. Technically it is covalent, but still it's essentially that H plus combined with a Cl minus. A base, on the other hand, is just a cation. Okay, so a positively charged ion combined with a hydroxide, okay, or multiple hydroxides, doesn't really matter. And a good example of that is NaOH. Sodium is a cation. OH is hydroxide. Combine them together, you form NaOH. When you put that in water, it's going to release those hydroxides, and that's what we consider to be a base. So then a neutralization reaction, all we're really looking for is we're looking for a metal combined with a hydroxide, and then an H combined with an anion. Okay, and then what happens is the hydroxide, the OH, combines with the H to form H2O. And then the remaining, the cation and the anion, then they are what's left in solution, and that is what we call a salt. Anytime we have a metal cation and a nonmetal anion. We call that a salt. Even though the most famous one is NaCl, table salt, sodium chloride, potassium chloride is also a type of salt, okay? Now, this one down below is one that's just a little bit trickier only because it's the one cation that we have that is not made of a metal. So this is on our list of polyatomic ions, NH4+. We call this ammonium. Okay, so we have ammonium hydroxide combined with, this is called sulfuric acid, okay, and that will form ammonium sulfate and H2O. So one of the big things you're looking for with a neutralization reaction is the product is going to be H2O, and you're going to see these hydroxides and an H combined with an anion as part of your reactants. And so look for those clues to figure out that you have a neutralization reaction. For sure, you always have H2O as a product. Okay, so here's the big final step of the day. What we're going to be doing is trying to actually predict what is going to form in each of these cases. So I'll have some questions here to ask you about some different ones of these and maybe give you some other examples. But in this case, let me see if I can switch this over. Why is this not switching? Pause. Okay, so this takes a little bit of trial and error, I guess you would say, to kind of figure this out. But you look at this first one here and you say, okay, hydrogen and oxygen. How are hydrogen and oxygen going to combine? Well, you know that hydrogen is, one atom here. Oxygen has 1, 2, 3. Let's try that again. Do it right. 1, 2, 3, 4, 5, and 6. And you're like, oh, how are they likely to combine? Well, we know that the hydrogen, they want to share there, and another hydrogen here wants to share there. So they're probably going to combine in a 2-to-1 ratio. This is going to become H2O. And this, of course, is going to be, what do we call this? This is called a combination reaction. Combination, again, it could also be called synthesis. Combination reaction, and then of course we have to balance this. We've got the 1 oxygen on the right, so we've got to put a 2 here to balance the oxygens because we've got 2 on the left. And then now that we put a 2 here, we've got to put a 2 here to make our hydrogens balanced. And so we have just shown how hydrogen and oxygen combine to form H2O. That's a common reaction, and that was again what we saw earlier on when we saw the Hindenburg blow up. It's because of that reaction. Okay, the next one here is we've got, and if we notice here, we've got 1 on its own, and then we've got the 2 here dancing with each other. So this is starting to look like it's probably going to be a single replacement. Now, the question is, which one replaces which? Remember that if we have something that likes to form an anion, it's got to replace the anion. You can't have an anion replace the cation. That wouldn't work. Okay, because then we'd have a negative and a negative, and that would repel. That's not going to work. So what's going to happen here is we are going to say, okay, well, what's that going to become? Well, we know that bromine wants to form a Br minus, okay? And so let's assume that. We know that Na wants to be an Na positive. So what's going to happen then is bromine, try that again. We always have to put the metal first. So we've got NaBr. Okay, so that is one of our products. And then now iodine is left on its own, and it's no longer an ion anymore. Now it is just on its own, except for one thing that's really important. Remember, as you can see from the periodic table in back, iodine is one of those elements. Let me make sure I'm showing it right. Oh boy, I can't angle myself right. There we go. It's one of our 7 that is included as diatomic. So we know that iodine needs to become I2. Now we need to balance everything because this becomes a 2 here. And let's see here. And this has to become a 2. And then I think we're good. All right, we're now balanced. Okay, so that is an example of a single replacement because iodine was replaced by bromine. Okay, now technically we would need to check our reactivity series card to make sure that bromine is higher on that reactivity series card than is iodine. But we do know that that is the case in this case, and so we know that that happens. But normally we'd have to look at that card, so we probably should have switched back to look at that. Well, let's do it. Just make sure you know how to do it. 1 second here. We'll do it later. My switching thing's not working so well. Okay, so now on the next one, we have something with an OH in it, and something with an H plus in it, essentially. And so what's going to happen? This looks like a neutralization reaction. Okay, so what's going to happen is the H plus and the OH are going to combine to form H2O. Okay, normally we put H2O second, but it doesn't really matter. Okay, and then the next one is going to be NaCl. Okay, so this is what we call a neutralization reaction. And then finally, this one is we have sodium sulfate and lead nitrate. Okay, so we don't actually have enough. You'd have to have enough, a little bit more information to know that lead and sulfate are going to form a solid. Okay, so we would have to be provided a little bit more information to know that those are non-soluble. But the fact that they put these together, we clearly have a cation dancing with an anion and another cation dancing with another anion, and probably this is going to be a case where things switch. I happen to know in this case that lead and sulfur come together to form a solid. So that's going to be PbSO4 is going to be your solid. Okay. Now you wouldn't necessarily know that, and that's completely fine. But we would give you some information so that you could know that lead sulfate does form a solid. How did I know that those were a 1-to-1 ratio? Well, we know that lead is a Pb2 plus, and the only way we know that is because we know that NO3 is a 1 minus, and we have two of them. So we've got two NO3 negatives. That means that's 2 minus on the negative side. Therefore, the lead must be a 2 plus. And then we can look on our polyatomic ions list and see that SO4 is a 2 minus. Okay, so SO4 is a 2 minus, so then it would be a 2 minus here combining with the 2 plus to form a lead sulfate, a 1-to-1 ratio between those ions. And then, of course, we are left with NaNO3 because both of those are Na is a +1, NO3 is a -1, so it's just a 1-to-1 ratio there. Now, the final thing we have to do, of course, is just balance this one, and so we can do that pretty quickly. We just have to say, okay, and you can kind of balance these in a way that you can look at these nitrates as sort of one group. So we know we have 2 nitrates on the left. That means we need a 2 right here. And then we have now 2 sodiums on the right and 2 sodiums on the left. So we're good there. And 1 sulfate group on the right, 1 sulfate group on the left. So now we are balanced. Okay, and that actually concludes our presentation for the day. And what we'll do is I'm going to put one other video that you finish, and I think that as you practice these, you'll be able to get them down. But this is actually a fun part of chemistry where you're actually starting to figure out what will happen. And we'll try to give some actual laboratory examples so you can see what each of these actually looks like, even though you've already seen some of them anyway. Have a great day. We'll talk to you later.